Connor, I think you're muted. Your microphone's got a red line through it.
Hello, hello, hello.
Now it's good.
Okay, sorry about that.
No
Small
problem.
technical difficulty.
Yeah, at least Zoom gives you an option. It says request that your other party unmute themselves.
Yeah, I didn't plug it in all the way first, and then it muted me. So
we haven't talked about the squeeze theorem yet. Can I cover it in 5 minutes?
Yes, I was gonna say yeah. Let's cover it in 5 minutes. I kind of wanted to modify that, but
It's not an important theorem, at least not for the rest of your calculus career. I don't know why they even include it. I guess it's a little bit like the epsilon delta definition of limits. Squeeze theorem pretty much says the following. I can sum it up in 2 minutes. And then that's pretty much all there is to do. There's no real problems.
And I think, to be fair, I think I have a good grasp, but I just want to go. The only reason I'm bringing this up is because I know it's going to be a question on the test. So that's, I confirmed it with the teacher. So anyway.
Call this f of x. Call this one g of x. And we'll call this one h of x. So, if they tell you that h of x is always less than f of x, and always greater than g of x, and furthermore, if at a point C the limit is L, in other words, if you now say that the limit of g of x as x approaches C is equal to L, you can see that on the graph.
Mm-hmm.
And if you also say L is the limit of the top one, f of x, also, as x approaches C, then even if you cannot calculate the limit of h of x, you know that it has to be L. In other words, h of x may be a function that you're not able to directly calculate its limit. But knowing that it is between the top blue function and greater than the bottom blue function, and that both of the top and bottom blue functions approach L as x goes to C, then the limit of h of x also has to be L as x goes to C.
Okay.
Now, that's all it says in my book. It doesn't give you problems to do. It seems like I have seen a problem involving the squeeze theorem before where they actually gave you the two functions, f of x and g of x, and maybe even the h of x, and you were able to calculate the limits of f of x and g of x, but not h of x. And so the only way you can calculate the limit of h of x is the fact that it's squeezed between f of x and g of x at all places.
Okay.
Therefore, it has to be, the limit of h of x has to be L also as x approaches C. And that's pretty much the squeeze theorem in a nutshell.
Okay, and that's more or less how I understand it.
Yeah.
So I have an example we can do before I get to that though, because this all kind of applies to screw it. Let's just do one example here.
Okay.
sure I understand. So this was the problem that I had that I solved for. And it's as so for the function of x sine x over or 1 over x. So that's
Hold
all
on. So we're going to make this f of x equals what?
x times sine of 1 over x.
Okay.
And then it's the limit for that function as x approaches 0.
That's the question.
That's the question. So then it's asking just to use the squeeze theorem.
Okay.
So let me just explain what I did, because I'm basically just making sure. I feel like I understand this. I don't think it's a crazy concept. I just want to make sure I have a grasp, right? So what I'm assuming this is happening between is that sine oscillates between -1 and 1.
Right. So that limit doesn't exist.
Right, or it would
As
be
x,
0.
as x goes to 0. Fine. If you're going to bark, you got to get out. Out. Go. Sorry about that.
No worries.
So that limit doesn't exist, and even if that were something like infinity, you'd still have 0 times infinity, and that
Okay.
is indeterminable also.
Okay, so the correct answer to this question is there doesn't exist a limit.
Well, not necessarily.
Okay.
In other words, you have an indeterminable. You can't tell what the limit is from this problem alone. So what they're going to do is they're going to try to ask you to figure out a function that's always greater than f of x, where you can figure out the limit, and another function that's always less than f of x, where you can figure out the limit. And then because of the squeeze theorem, you can figure out the limit of this one. Now,
Okay.
what might those two other functions be? That is a good question. Do you know the other two functions for this problem by chance?
No, because it literally just gave this one by itself. This is
So, I think I do have a calculus book that has a similar problem like this. It might be this exact problem. But the secret is going to be to find a g of x that's always greater than f of x, and to find an h of x that's always less than f of x. And g of x and h of x, you will be able to figure out the limit as you go to 0.
okay.
In other words, there will be a standard function that will give you a limit for that. And then based on the squeeze theorem, you'll be able to figure out that the limit of f of x is the same as those other two. In other words, what's important here is that the limit of g of x be the same as the limit of h of x as x goes to 0. Now, without giving this more thought, I'd have to spend some time trying to come up with what these functions might be. But that's going to be the secret.
Okay. Okay. And I think that works.
If I look at my other calculus book, I think I'll find this problem, and I can help you further with it. But rather than wasting our time on it right now, because it could take 20 minutes experimenting around with functions such that these two conditions are met and such that the limit of each of those is defined as x approaches 0.
Okay. Well, I'll tell you what. Let's table it, because I do want to see you one more time before I take the test.
Okay.
And so that might
let me
be
do a
something
little research and
to circle
and
back on. And I'm also going to review it.
Yeah, I'm recording this, so I can always figure out what it is. Okay.
Okay. So
intermediate value theorem. Let's cover it just very quickly.
Perfect. Yes.
If you have a continuous function,
and it has to be continuous.
Then you cannot get from A to B without going through all points in between. It's as straightforward as that.
Okay.
It's not a theorem where they give you problems to solve. It's more of an existence theorem. It's kind of like saying you cannot get in your car and go from 20 miles an hour to 60 miles an hour without going through every speed in between.
Okay.
In other words, you cannot skip from 30 to 40 miles an hour. If you had a non-continuous function, like that, well, now the intermediate value theorem doesn't apply, because I definitely, between A and B, there's all kinds of points here that are not on there.
Okay. Okay.
And that's that in a nutshell. And I wouldn't worry too much about those two, the squeeze theorem and the intermediate value theorem. You may get a, like you, professor told you were going to get a squeeze theorem, so we probably should pay attention to that one. But the intermediate value theorem is more of a theorem they just kind of give to you as an existence theorem. I've never actually seen problems that depend on the intermediate value theorem. It's used more for proving more advanced theorems in calculus. There's a lot more advanced theorems to come in calculus, and the proof of those theorems sometimes uses the intermediate value theorem, things like that.
Okay. Okay. And that's kind of what she's going to be using this one as. This is similar to the squeeze theorem, where I'll have a function to test if it's continuous. And if I test it's continuous, I test the endpoints, or essentially, where the interval is from where from which it's continuous of, and then see if the theorem applies. But that's literally it. So yeah, I didn't want to spend too much time on it. It's just something to highlight real quickly, just because these are going to be questions on the test.
And the third subject that I don't cover very often is this second definition. Let's talk about it, because I bet you have at least one problem on here also for this. In other words, the standard definition for this is the limit quotient theorem. F of x plus h minus f of x all over h as h goes to 0. There is a secondary definition of it, and that definition is f of x minus f of c all over x minus c as x approaches c. Now, where might this be used? Here's a good example on this one. If we take the function f of x equals the absolute value of x minus 2, which, if I graph that, basically looks something like that. Okay? And for a function to be differentiable at a point, it has to be continuous. And for a function to be continuous at a point, the limit from the left has to equal the limit from the right. And if we try to figure out if this function is differentiable over that cusp or corner, is what they're called, then we would try to use this particular definition for first derivative is used mainly to prove that this is not differentiable through that point. Okay, and here's how it's proved. First of all, for it to be differentiable, the limit has to exist. Okay. And if I take the first derivative of the left side of this, I get the limit of Well, f of x is x minus 2 minus 0 minus f of 2, right? According to this, f of 2 is 0. And if you solve that and you seek the limit as x approaches 2 from the left, that limit is equal to minus 1. Based on that definition. And if you take the limit of that absolute value function all over, no, hold on, I needed an x minus 2 down here in the denominator. And here I have the same x minus 2. But in this case, we're taking the limit as x approaches 2 from the right. And we can see that if we're approaching 2 from the right, the slope is positive 1.
Okay. Okay.
Since the limit from the left is not exactly the same as the limit from the right, then the limit does not exist at the point 2. And if the limit doesn't exist there, it's not, it's not differentiable. Yeah, this is not so much to prove or disprove continuity as much as to prove or disprove that a function is not differentiable at a point. And another function that is a good example of this is a function that has a vertical limit. In other words, something that looks like this. And that function would be x to the 1/3. That's what that looks like.
Okay.
And if we look at x equals 0, and we try to figure out the derivative there, the derivative does not exist, and therefore the tangent line has a vertical slope. And if it's a vertical slope, then its first derivative does not exist at x equals 0. It's still a function, incidentally, because it does not violate the vertical line rule. In other words, x to the 1/3 is absolutely a function. It's not, the only thing is it's not differentiable where it has a vertical tangent line. And it has a vertical tangent line right there. If I were to draw a tangent line through there, that's what it would look like.
Okay.
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 And so this alternative definition here is used when you're trying to prove whether a function is differentiable at a certain point. And we just proved that it's not differentiable here at x equals 0 and at x equal 2 on the absolute value function, it's also not differentiable.
Okay. And those are the two main cases of it
Oh, those are the two that are in my book as an example of when. It's the only time you ever use this function. Because this function gives you the slope of the tangent line at a point.
Okay, and then so the one that's h or x plus h is the actual function.
That'll give you the first derivative as a function.
Okay.
Okay. In other words, I can take the first derivative of this function. If I just use the power rule, it's 1/3 x to the negative 2/3, which is equal to x to the minus 2
over 3.
over x to the 3x to the third. And let's see, do I have that right? No, I don't. What is that? That is no, it's 1 over, sorry, I got it. Yeah, I got it backwards here. It's the derivative of that function is 1 over the square root of x. 1 over 2 times the square root of x.
Okay.
And this function, you can see, is not defined at x equals 0. It is defined at all, it's actually not defined for negative values either. Oh, I realized I'm looking at the wrong thing here. Just a second, I screwed this up. Yeah, I was right here, hold on, let me back up here before I really screw things up here. The derivative of that, using the power rule, yeah, no, is 1 over okay, so let's go back and use this proper definition here. There's the graph, and there's the function. So how would we take the derivative? We haven't been taught the power rule, so we can't use the power rule. So what it is the limit of f of x, which is x to the 1/3, minus f of c, well, f of c is 0, all over x, since c is 0, and we're taking this limit as x goes to 0. Well, that's x to the 1/3 over x, so subtracting exponents gives you x1, actually gives you x to the minus 2/3, which is the same as, it's infinity as x goes to 0. Okay, so if I solve this, and then I substitute x in for 0, or 0 in for x, I can see that the denominator goes to 0, the numerator stays at 1, because this is the same as 1 over x to the 2/3. And if you want to know what that limit is as x goes to 0, x can be all numbers on the number line except 0. Only at 0 does this thing go to infinity. So since its limit is infinite, it means the slope of the tangent line has to be vertical.
Okay. Okay. Quick question.
Yeah.
We went from, is it because we're doing 1 over the square or x to the 2/3? Is that why we get rid of the negative sign?
That's the same as this. When you have a
Right.
negative exponent, it just means you put it 1 over x to the positive exponent.
Okay. Okay. Just want to follow. Okay. And this
that's the only time you use those, because with any other kind of function, you just go ahead and you use the other definition, the more robust one, f of x plus h.
Yes.
And you get an answer that is a function, just like that. And I would have got that if I'd have used the other definition also. But this definition does tell you that the one number x cannot be is 0, because this limit goes to infinity. And when you have an infinite limit, that means your slope of the tangent line is vertical at that point.
Okay.
All right. These things that we've covered so far in today's session are not, you don't,
She told me that
the
the
squeeze
reason,
theorem never comes up again.
yeah.
In
So
3 years of calculus, they teach it to you in the beginning just to tell you about it, and then you never see it again.
she literally told me it's on the first exam and it's on the final, and that's the only time that
Yeah.
she teaches it.
And
So
this is probably the same thing.
right.
Um,
It's the way that it's the curriculum is
this particular
structured.
alternative definition of first derivative, you could use it at a point. You could take any function and say, well, what's the derivative as x goes to 2? And you could use this to solve for it. But you wouldn't, because we're used to using the first definition, and the first definition will then let you find out the slope of the tangent line no matter what x is. So it's far more robust. And the intermediate value theorem, you just don't use it. So these last 3 things, or these first 3 things we covered, they may be on your exam, but they're not fundamental for calculus to follow. They're not. They just aren't. I don't know why they demoralize everybody by giving them to you in chapter 2. Because that's where they are in my book, too. You don't really get into real calculus until chapter 3. And I shouldn't say real calculus. It's real calculus. It's just not fundamental to any of the problems you'll have for the rest of the year.
Yeah. Well, I apologize. If it was up to me, it wouldn't be a thing, but I just want to make sure I do well.
No, I wanted to cover it because I know you're going to be tested on it. But I also want you to realize that it's not like you can't make your way to more advanced calculus without understanding these. You can. You cannot understand any of these 3, and you'd be just fine. You may miss those questions on the test, but it's not going to prevent you from going forward in calculus. None of them.
Okay.
Okay.
So I wanted to do 2 things now. I'm hoping to kind of hit 2 birds with 1 stone.
Okay.
I have a question. This is for limits at infinity.
Okay.
So this is the question. Let me just get it on paper here. So it's the square root of x squared plus 13x, and that's all over 5 minus 8x as the limit as x approaches negative infinity.
Yeah. Okay. So here's how we're going to do this. We can't take the square root of x squared plus 13x. You can take the square root of x squared, but when you add the 13x to it, I can't take it. But whenever x is going to infinity, the only terms you need to care about are the largest degree polynomial. In the numerator, it's that one, and in the denominator, it's that one. And you can essentially ignore that and that.
And that's like a general rule?
Yes.
Okay.
And when you do that, the numerator becomes just x. The denominator becomes this. And now the limit as x goes to infinity is the ratio of their coefficients. It's that straightforward.
Okay, and that's right. Okay.
Okay, you got another one?
Similar, yeah. This is so I guess let me get it down. There's something I wanted to ask about interpreting graphs, I guess is what I'll say. But anyway, so this is the function is 8e to the negative 0.2t power plus 3.
Plus 3 in the exponent?
No, I'm sorry. That's it for the exponent, and then it's just plus 3.
Okay.
I think I know what to do here. I just want to confirm. We can.
Okay. Well, let's start by taking the e to the negative exponent and making it e to a positive exponent.
You can just put it underneath. All right. Okay. I think that's that simple, because then t becomes infinite, which means it's basically 8 over 0. So it'd just be plus 3.
correct.
Okay, cool. Okay, so this is very basic, Mr. Cohen, so you're going to have to forgive me. I got to freshen up on my algebra and some of my, actually mainly just my algebra.
No, that's a big part of calculus. Is there's a lot of hard algebra in it.
So when it comes to an equation, you know, or something you would have to picture graphically to understand how to answer some of these questions. I don't want to go over maybe the main styles of ones because that's easy enough to Google. But for example, like, you know, if your denominator has, I guess let me ask this: is there an easy way to infer what your vertical and horizontal asymptotes are in an equation? I think for the vertical, it's whatever's in the denominator, right? Like
It's whatever makes the denominator 0.
Okay.
Those are your vertical asymptotes.
And then for horizontal, is it just equaling to y?
Let's take this. In other words, we started out 1 over x squared minus 1. Okay?
Okay.
And that becomes these. So if I want to graph that, the very first place I always start is the vertical asymptotes. Well, what makes the denominator 0 when x is either 1 or minus 1?
Right.
So I've got a vertical asymptote there. And vertical asymptotes cannot be crossed. Horizontal asymptotes can be, so can oblique ones, but vertical ones cannot. And as long as the denominator is a higher power of the function, of the variable, x squared, the numerator is x to the 0, basically, then your horizontal asymptote is always y equals 0. So there's my grid that I would start graphing this thing on.
Okay.
And this looks like it's going to do something like this, maybe. And then in between, what's going to happen in between? These things usually they look like this, kind of. If I were to look this up on Wolfram Alpha, I'm not sure that would be the exact graph.
It's pretty close. I just typed it
yeah,
in.
it should be pretty close. And what goes on in between your vertical asymptotes is always the problem. Because sometimes what goes on in between is a line like that. And then this part here will be down here or something. But you always start with your vertical and horizontal asymptotes and set up a grid. And then what you're looking at is a hyperbolic function. So it's always going to take the form, the same. This is your basic hyperbolic function, 1 over x. If I graph that, looks like that. And if I were to graph 1 over x squared, it would look like this instead. And if I graph 1 over x squared minus 1, it looks, I'm not sure which one of these. It sounded like this one maybe matched what you were looking at in your book or something.
Yeah, no, this is pretty good.
Okay.
So again, just to clarify something for me,
the way you could actually tell whether this middle part crosses the x-axis or not,
okay, yeah,
is by seeing whether y is ever 0. In other words, is this function ever 0? Because for that middle part to cross the x-axis, you would have to have it be 0, right?
Right.
And if 1 is the numerator, then it's impossible for that to ever be 0. So I know that it does not have an x-intercept. And that takes me a long way because it's squared, I know these two parts are in quadrants 1 and 3. And since it cannot cross the x-axis because this will never be equal to 0, then it must do this, like I drew it.
Oh.
If you find that there is a solution where it can be 0, then you know it crosses the x-axis, you can figure out where it is, and it probably looks something more like this.
Okay.
And then what it does, usually on the other side of the asymptote, it almost always comes out the other. In other words, this thing is headed towards positive infinity. So when I get on the other side of that asymptote, pretty sure it's going to be coming up from negative infinity. So you could have a lot of hyperbolic functions that would look like that. But for it to look like that, it's got to be able to cross that. Notice it does cross the horizontal asymptote. And that still would have a horizontal asymptote at y equals 0. But the way you tell is, first of all, you plot all your asymptotes, and then you look and see if there's any x-intercepts. And notice in this function there are no x-intercepts. And for there to be an x-intercept, y has to be able to be 0. And there is no value of x that you can put in there that makes this function equal to 0. As long as you have a number in your numerator, it's never going to be equal to 0. Because
now I was just going to ask if I
0, you have to have 0 in the numerator.
And I was just going to ask if I'm ever unsure, I can plug in points for x and just build the graph and
Yes,
kind of get it. Yeah,
absolutely.
Okay.
Absolutely. And that's the way you generally do these. But after you've done a number of them, you kind of remember what pattern they tend to look like. And you can kind of do it without making a table of points.
Gotcha.
Okay, what else?
Let's see here.
The derivative of a constant is always 0. Why is that? Because if I say y equal 3, it's always a horizontal line. And the derivative of a horizontal line is always 0. The slope.
Gotcha. Okay.
The slope of a horizontal line is always 0. And slope and derivative mean the same thing.
Right. Okay, this is another quick one. Hope I'm assuming here. But anyway, so the function is 3x to the 4th as the limit of x approaches infinity.
Obviously, infinity. In other words, infinity to the 4th power is still infinity, and infinity to the 4th power times 3 is still infinity.
Okay. So now, here.
If I'm approaching negative infinity, then this exponent matters. In other words, if I change this, the answer is still infinity. Because negative infinity to the 4th power becomes positive infinity. If I take negative infinity to the 4th power, that negative sign goes away and it becomes positive infinity.
Interesting. Okay.
If it's to the 3rd power,
it'd be negative.
Yes.
Yeah.
Okay. In other words, if it's to the 3rd power, then minus infinity cubed is still minus infinity times 3 is still minus infinity.
Okay, real quickly, because this is actually, so I was told something yesterday, and this really piqued my interest. So this is actually the same. This is a slightly similar equation now, or function. Okay, so go ahead. That's fine. So it's 3x cubed all over 3x squared minus 2. As x approaches, as x approaches negative infinity.
Okay. again, this is a situation where the numerator rules, right? I can ignore the minus 2.
Okay.
When I'm talking about x going to either infinity or negative infinity, I just eliminate anything but the highest degree polynomial. So the
top and
only
bottom,
thing I'm
right?
really looking at is that.
Okay.
That reduces to x. So as x goes to infinity, that goes to infinity.
Okay. So the answer
X
for
goes
this
to
is
minus
infinity.
infinity, that goes to minus infinity.
Awesome. Okay. Okay. All right. So gonna step it up a little bit now.
Okay.
This is probably more work per se, and maybe give me one
Depends.
sec.
This calculus right along here actually gets quite a bit easier as you go forward.
You told me that the other day.
Well,
so...
we're not forward enough yet. What I kind of meant was when you get to a point where they're teaching you the power rule and the product rule, that's when you're forward.
I guess this is 2-6. 1 second, Mr. Cohen. I apologize. Let me make sure I'm looking at the right one here. Okay, so this is going to be using that first derivative, or the first derivative of the function. Okay. So
The f of x plus x h.
Yes.
Okay.
Yes. And so one of the things that, and this is weird and goofy for me. Anyway, let me explain this function. The function is the square root of 2x minus 1. And for some reason with this kind of stuff, I always get confused on what I'm plugging in for what, if that makes sense.
Here, let me make it real clear. The way you always start these problems is by defining that, and then defining that, and then just substituting. So if this is f of x, we've already defined that. What is f of x plus h?
So then that should be then 2x minus 1 plus h, right?
The square root.
The square root
of 2 times x plus h.
That's
minus 1. In other words, whenever you have a function and they stick something in the parentheses other than x, whatever it is, no matter how complicated or big it is or whatever it is, you just substitute it in for x.
Okay, thank you.
Okay. And now that becomes, substitute. Since I know what that is the square root of 2x plus 2h minus 1. And then I'm going to subtract from that the square root of the original function, 2x minus 1. I'm going to put it all over h. And then I'm going to take the limit of that as h goes to 0. Now, the algebra on this.
So this should be the conjugate rule, right?
The what?
We should be multiplying by 1 to get rid of the square roots.
Yeah.
Yeah?
Yeah.
Okay, quick question. Quick question, because that part I get. So I'm with you now on following the logic. I'm just not totally there. Where did the 2h come from? Is that because we're distributing the 2 to the x and the h?
Okay, if you start with that, the very next step is always to figure out what f of x plus h is. Okay. That was my first step. The next step is to figure out what f of x is. Well, they gave us that, so that was actually given.
Right.
And then we just substitute. And then we have a limit problem that's got radicals in it. And as you correctly surmised, the way we're going to get rid of those radicals is to multiply by the conjugate. And the conjugate in this case is square root of 2x plus 2h minus 1 plus the square root of 2x minus 1.
Ah.
I'm going to multiply the bottom by that and the top by that. So, yeah, you always want to have lots of paper to write on when you're doing
Yeah.
these. Seriously. In fact, when I first started tutoring calculus, I actually went out and bought legal paper, 14-inch long, because I needed 14 inches instead of 11 inches to be able to do these calculus problems. So I'm multiplying the top by that and the bottom by that. So I'm multiplying this fraction by 1. I can do that. And when I multiply by the conjugate, the top is going to turn into 2x plus 2h minus 1 minus quantity 2x minus 1. And remember what I always told you, is that when you simplify that numerator, every term that does not have an h in it will go away.
Okay.
In other words, the 2x minus the 2x, this minus 1 on the far right becomes a plus 1 because it's a minus. So the 1's go away. And what am I left with on the top? I'm left with 2h all over h. And then the h's go away. That thing goes to 2. Now, let's see if we can duplicate that, prove that using the power rule. In other words, the power rule will confirm my, it was 2x plus 1 or minus 1? It was 2x minus 1, right?
Yeah, squared, or square root.
Square root. Okay, so if we apply the power rule here, we multiply this whole thing by the exponent, and then we subtract 1 from the exponent. And then this actually requires the chain rule.
I'm not familiar with that one.
No, you haven't been taught the chain rule yet. That'll be the 4th rule they teach you after the power, product, and quotient rule. But it means that I have to multiply this by the derivative of the inside. What I just took was the derivative of the outside, and now I have to multiply the whole thing by 2. And that 2, which is the derivative of that, and that 2 cancels with that.
Mm-hmm.
And so now I'm left with 2x minus 1 to the negative 1/2, which is the same as this, square root of that. So it's 1 over the square root of 2x minus 1. Now, I don't think that's what I got when I did it the other way.
Right. It was just 2.
Yeah, it was just 2. And don't know where I made my mistake algebraically.
I was going to point this out. I don't think that we distributed the bottom half of the conjugate to h.
Ah, you're right. I left the bottom at h, and it should have been h times that conjugate.
Right.
Ah, and if we do that, we'll get this answer.
Okay. Okay.
Yeah.
Well, that's good.
And you always have an h when you're done, but then you let h go to 0. And then you usually have something else. Yeah, that's what I did wrong.
Well, and then likewise, so I did this to ask this, okay? So, or ask this to ask that, however you want to say it. So essentially, though, once we've gotten this first derivative of the function, as you pointed out before, where we were always going with a point, I could plug in any point for x to figure out that point.
Yes, you can figure out the slope of the tangent line at any x.
Yeah. Okay.
Whether
cool.
x is 0, 1, 2, 3, 4. Whereas if we were using the alternative definition, that will only tell you the derivative at a specific point. So it's far less useful because it just gives you the
Right.
slope of the tangent line at one point,
At one
whereas
point.
this gives you the slope of the tangent line along the entire domain.
And that's what you meant by it's far more robust.
Yes.
Okay, that I follow you now. Okay, cool.
Yeah, this domain is virtually all positive numbers. A little bit different, but so I have an infinite number of points. I can tell you the slope of the tangent line for this function. Yeah, since you don't know the chain rule, yeah, you really have to use that other definition to actually solve this one.
Yeah, and that's unfortunate, but again, she literally told me it's being tested on the exam for the first one, and then the rest of the semester is with actual derivatives,
Yeah,
and then the final.
yeah. Let me. I think I can correct my mistake. Really simple that I made here, because if I remember right, that conjugate was minus 2h minus 1. So that might be what we actually end up with. But then if you take the limit of that as h goes to 0, you get 1 over the square root of 2x minus 1.
Right.
And that's usually the case. When you use that limit quotient definition, the first one, you generally end up with an h. The h's don't all disappear usually. But it's an h you can handle, because now when you go back and substitute 0 for h, it doesn't give you something that's undefined. In other words, if I take the limit of this function that I've got on the right side, I can now, that's what I got when I used the limit quotient rule. So I'm still taking the limit as h goes to 0, only now when I plug in h goes to 0, I get 1 over the square root of 2x minus 1.
Okay, cool.
Which is the answer. This chain rule, let me just explain it to you in a nutshell, because I can get you to understand it in 30 seconds. If I want to take the derivative of that, verbally, it's really simple. You take the derivative of the outside and you multiply it by the derivative of the inside. Well, the outside would be 4 times 3x squared minus 1 to the third power. And the derivative of the inside is just 6x. That's the answer.
Oh, okay.
So the chain rule is basically fairly easy. Same thing as if I had, if the function is the sine of 2x, there's my function. Well, what's y prime? The derivative of the outside would be the cosine of 2x, right? Because the derivative of sine is cosine. But the derivative, that's the inside. And the derivative of that is 2. So I multiply that by 2.
Okay.
That's the chain rule in a nutshell. Now, when they explain it to you, they'll make it a lot more complicated than that. And then after they've confused the hell out of you, they'll tell you, just think of it as the derivative of the outside times the derivative of the inside. And it can be used multiple times. There can be multiple insides when you're talking composite functions. This is a composite function. The sine, it's a combination of sine x and y equal to x. So whenever you have a composite function, you're going to apply the chain rule. The derivative of the outside times the derivative of the inside. Just always remember that, and you'll get it down pretty quick.
Okay. Okay. All right. If we've got time for one more, I just wanted to do one more. This is infinite limits question. Okay. And this might be easy. I just wanted to see this. So cosine of 2x all over sine x as x approaches pi. Yes. It's a little different.
Okay, so if we do a direct substitution, the cosine of 2 pi is 1, and the sine of pi is 0. So with a direct substitution, I would get 1 over 0, so
it's not determinable.
Does not exist.
Okay, okay.
And you might say that it's infinity, but it probably isn't, because if I go from the left or the right, it's probably negative infinity in one case and positive infinity in the other.
Okay.
So it almost certainly doesn't exist.
Okay. Okay. Well, how about this one then?
Okay.
Last question.
You can keep
so
going until 5 at least. Go ahead.
That's true. So 2 secant of 2x as the limit of x approaches pi over 4.
Okay, the way to verbalize this problem is you are taking the limit of 2 secant of 2 pi x, right? Or is it 2x?
Oh, no, I'm sorry. It is x. I apologize. It is x. 2x.
And we need a variable in there somewhere. Otherwise, that's just a constant, and the limit is 0, or the derivative is 0. So, and this is as x approaches what?
Pi over 4.
Which means the secant of 2x is going to be the secant of pi over 2. Secant is the reciprocal of cosine. The cosine of pi over 2 is 0. So the reciprocal of 0 would be 0 in the denominator, undefined.
The cosine of pi over 2 equals 0, you said?
Yeah, here, let me there's the cosine curve. And because we know that secant is the reciprocal of cosine, then secant sits on top of the peaks and the valleys. And the secant has asymptotes. In other words, whenever cosine is 0, the secant is undefined.
Okay.
Because it's the reciprocal of 0. You can't take the reciprocal of 0. So the secant of 2x at pi over 4, well, here's pi over 2 right there. So you're talking about what happens to this as we approach pi over 2, goes to infinity. But on the other side, it goes to negative infinity. So the limit from the left is not the same as the limit from the right, therefore it's undefined.
Gotcha. Okay.
Now just to be clear, there's one very common case that I think I've mentioned this one before, but that's that graph. If I said, what is the limit of that as x goes to 0? Well, as x goes to 0 from the right, it's positive infinity. As x goes to 0 from the left, it's negative infinity. They're not the same, therefore the limit is undefined. However, if I make my function this, and I want to know what happens as x goes to 0, First of all, that graph is like this.
Okay.
And now, as I approach 0 from the right, the limit is infinity, positive infinity. As I approach 0 from the left, the limit is positive infinity. So they are the same.
So it's infinity.
So, yeah, so in my book, that means it's infinity. But you, I believe, had this problem not long ago, and they told you it was undefined. And you had a problem similar to this. And this is, I think, more a question of terminology. A lot of math teachers just don't like the word infinity if they can use the word undefined. But I've read other calculus books that say this one most definitely does not exist, and then they follow it up with this one most definitely does exist, but they're not willing to go so far as to say that it's infinity.
Okay.
But they say it definitely exists because the limit from the left is the same as the limit from the right.
Gotcha. Okay. Okay, cool.
All right, any last questions?
No, I have 2 saved. So I think it'll be a shorter session.
Okay.
Because I did want to just analyze. I know it's not super imperative to the concept or the realm of calculus per se, but because it's a test question, I did want to do the squeeze question.
We're beyond all the tough stuff. We are. I'm looking at my book, and everything else from here forward doesn't have these fuzzy conceptual difficulties like squeeze theorem, intermediate value, that alternative definition, cusps, corners, all those things.
Okay. Okay, that's good to know. So yeah, I want to do an example of a composite question and the squeeze theorem question.
If I was teaching calculus, I would start on chapter 3, not chapter 1. Well, chapter 1 is limits, so I would do limits, but then I would skip over all this chapter 2 stuff you've been on for a week. Just because it's not necessary for the further stuff, and it's very confusing and hard to understand. And I believe stuff should be taught simple to hard, not hard, then back to simple, and then medium, and then hard, which is the way they teach calculus.
Yeah, it's the school system.
It really is. Well, it's all over. It's not just Colorado. It's the entire world. I've been tutoring calculus for quite a while now, and they all have the same curriculum. You start with limits, and then you deal with all of this esoteric stuff like the intermediate value theorem, the squeeze theorem, all that stuff. And then you get into the applications and reality of how calculus makes a difference in your life. And once you get to that point, you're using these rules to come up with first derivatives. And then they start applying them to real problems. And that's when it gets pretty fun, and it gets more difficult then also. But it's more easy to understand. Let me put it that way. It might be hard, but it's easier to understand than some of the earlier stuff that's hard and hard to understand.
Okay. Mr. Cohen, as always, I appreciate the time. I do feel pretty comfortable with most of the concepts, but it doesn't hurt to beat it with a dead horse sometimes. So,
okie dokes.
Have a good one.
Have a good rest of your weekend, and I'll talk to you next time.
All right, you as well. Thank you.